So, okay, so this is the title says the whole thing, the mystery. Because as far as I see, I'm concerned, you will see problems. And you'll see, no. Yeah, please don't talk in the audience, otherwise you attract my attention and I cannot concentrate. Okay, again, I have to, for the background, I have to suggest you to look at this monograph, and without its knowledge, it would be difficult to technically understand the rest of the lecture. This is the question number 2. There were 3 questions on the preceding my preceding lecture. Whether matter, antimatter attract or repel each other. I answered in the first question, in the first lecture. Question number 2 is whether we can see antimatter asteroids with the sun with matter light, or like this, or we don't, like this. That's the issue, open issue. And then the next issue is whether, the third issue is whether we can see a star, an antimatter star or galaxy, whether we can see it with existing means, such as available telescopes and so on, or we don't. Those are the issue that I'm trying to address here, and this is the answer. The answer is that I do not know. I believe this is the only scientific answer as of today. Any other answer is, not, in my opinion, not scientific, because it's based on some political idea of preserving Einstein or preferring a certain theory over another. There is no, not only theoretical, there is no any position, there's no resolutory, theoretical, experimental background. The only thing I can say is list the alternatives. If you assume Einstein theory as valid for antimatter, the question makes no sense, because the treatment, the theory do not treat any difference. The light is the same according to special and general relativity, whether it's emitted by a matter or antimatter is the same. The problem, however, the general relativity does not even address the issue of the gravitational field of an antimatter star. So even this position, in my view, I'm sorry, is not technically tenable. But nevertheless, it has to be historically presented. Again, over and over again, I have defend Einstein over Einstein fall over abuse his name. The poor fellow, I mean, poor Einstein is not a poor fellow, but antimatter was discovered a long time after his formulation of general relativity. So all this imbalance is certainly not due to Einstein, but it's due to interest on Einstein. But again, the issue is raised by this imbalance that we addressed the first issue, the first lecture, namely matter treated at all level, antimatter only at a level of second quantization. If you resolve this issue with isodual, then you start to see some problems. Because the consequence, again, the direct consequence of achieving a Newtonian or relativistic or gravitational formulation for antimatter, neutral antimatter, is that light emitted by antimatter is different than light emitted by matter. And difference in the very value of the energy itself becomes negative. Of course, careful is negative, but refer to a negative unit. So there is no inconsistency that we could identify. Then, in view of this physical difference, then there are other differences. This is called isodual light. There was a paper published a few years ago that enters in the other physical differences of isodual light. It's not only the energy and the gravitational point. Again, you see this. I believe Newtonian gravitation is universal. To be universal, then I start also apply on light. But light has no mass, so what? So what? That's why even from my graduate many years ago, that's the way I write Newton's equation in terms of energy, and then the gravitational constant is divided by the square of the speed of light. In this case, we're talking about the attraction of ordinary light by mass, which I believe the bending of light, in my opinion, is purely Newtonian. And you do the calculations, you get it perfectly well. Now, you can interpret also with curvature, but that's a separate issue. As far as at this level, And if it is not Newtonian, then Newtonian gravitation is not universal, and you have all sorts of other consequences. So in the same way as you represent the bending of light, you will represent the repulsion of light, anti-bending, I don't know the name. And this is unavoidable in this setting. So light, in the behavior of light emitted by matter and antimatter is predicted as having some consequences. Now, the rest I didn't have time to put it in a formal way, but I don't think I will try for the paper eventually for the proceedings. But here I want to bring to your attention some apparent inconsistency of the isodual theory. Because, for instance, one of the objections is, Ruggero, but here you have a gamma, there's a photon, and then this proton produces electron and positron. With the isodual theory, you violate the conservation of energy, because the energy of the photon, you get it only half in the electron, but you don't get the remaining half. It's not true. It's very tedious but very tricky. The reason is essentially the following. You see that when you see, this is the case for the electron. You have the Hamiltonian for the electrons, the energy, if you want, multiplied by the ket. Here, now remember, this is in our world. So the ket is one in our Hilbert space, or in our space-time, if you want. Then for the positron, you have a dual Hamiltonian. And then the multiplication is dual, but the ket is the same, because that's observed. They cancel each other. You end up with a total positive energy. So there is no violation of, as far as we can see, no violation. And if you do this in the isodual world, you'll get -1 electron volt. So there is no violation of any conservation law that I know. Also, we checked. This is very trivial, a little exercise. We are talking about a totally antimatter world. That the isodual light is certainly absorbed beautifully by antimatter atom in the ground state. Then the ground goes in what we call it excited, but careful, isodual excited, and then the isodual light is re-emitted. You do the calculation, it's trivial. But careful, that the binding energy of the isodual atom is positive, definite. In our case, is negative definite. In this world, instead, is positive definite binding energy. This caused some problems in detecting isodual antimatter galaxy and stars and asteroids. Now we start with the unsolved problems. So in other words, what I said until now, the antimatter world is totally, everything happens with us happens at the antimatter world. Now let's try to mix them. So here what we have a light. Light means light from matter that hits an antimatter atom. And we start to have problems. You see the question marks. I've been unable to achieve a final conclusion, even myself, even within the realm of the antimatter theory. So any of you who wants to look at this thing will be very, very appreciated. And the reason being because, you see, because we are talking about an antimatter atom in the ground state. But the binding energy is positive. So you have you add the energy of our photon, matter photon, with this positive binding energy. What do you get? It's not that clear. It's not that clear, because one possibility will be photodisintegration. Namely, we cannot exclude that the antimatter atom disintegrates. It's killed. It's killed, and you end up with separating the positron and the antiproton. Becomes because as far as the energy is concerned, yes, because in other words, since you in other words, in an antimatter atom, you cannot absorb a photon. You absorb an isodual photon, yes, but not a photon. Since you cannot absorb it, of course it could bounce off, yes. And then we see the asteroid, antimatter asteroid. But this is not the only solution. That's the solution that these things disintegrates. And then there are a number of other alternative solutions, such as for instance, so this is the conclusion that I bring to your attention. At this moment, the only thing that personally I know is that I don't know. I'm not 100% sure. Even by using isodual theory of antimatter, I'm not 100% sure that we can see an antimatter asteroid with sunlight. There are a number of other possibilities if you look deeper. For instance, that light is simply absorbed. If it is, it depends also on the temperature of this object. If this object has a certain temperature, then light could be simply absorbed without any effect whatsoever and no refraction at all. Or a number of other possibilities that if we list them all. And then we have to exclude those that are implausible or violate some laws and so on. But ladies and gentlemen, this is my conclusion at this moment. I do not know. Let's go now to whether we can detect faraway stars or galaxy made up of antimatter. And here we have problems. Let me at least elaborate. Those are all the possibilities. Suppose this is a lens, the lens of a telescope. Okay, and this is an antimatter light, isodual light. Then the only thing I can do at this moment to list all three possibilities, but I cannot exclude any of them. I have no information, theoretical or experimental, to make a selection. The first possibility that this is absorbed. Lenses in our telescope are not at absolute 0 degree temperature, and there are processes in which this thing can be absorbed into the anti-heat, isodual heat of the lens, and therefore have no refraction or propagation at all. This is the prediction for based on Einstein theory. Prediction Einstein theory is that you have a refraction and with an angle of refraction, but there are problems here, ladies and gentlemen. When the refraction is due to a decrease of the speed of light in a physical medium, when that's the very, very essence of so unless we have a decrease of the speed of light, then we don't have refraction. Well, ladies and gentlemen, these conditions imply an increase of the speed of light in this configuration. As crazy as it may seem, yes, because the speed of the isodual photon is negative. Being negative, when you are, you have to by decreasing means that in actuality in the isodual world the speed is actually increased. So this will be then the correct view for isodual theory, presumably, has to be yet to verified, because here, yes, we have a decrease in the speed of light. Of course, in absolute value. Remember, we have a negative value of the speed, which increases in absolute value. So therefore, it decreases in their own world. The more negative you go, the more. So this is a prediction that we cannot exclude at this moment. To our extremely limited knowledge that we have on this issue. That's why this is the first workshop on antimatter astrophysics, for very good reason, because we don't know the answer. Maybe in the future we can. Now, what are the complications? They are fun, they are very strange. This is an antimatter star and this is an ordinary telescope. I can only list the possibility. First possibility, that nothing comes out and we see nothing. The second, because light is so dim, there are processes in which it is absorbed and will not allow any propagation or refraction or whatever. The other possibility is Einstein, that indeed we see. But this is a possibility, this prediction from isodual theory cannot be excluded. Since that this lens is now divergent, is convergent for ordinary light, yes, of course, but it can become divergent for antimatter. And therefore, when you go this way, you don't see nothing. You don't see nothing with a telescope designed for matter light. Not necessarily you can see the light from an antimatter star. So this is the third conclusion is also there is an unknown, and therefore that's why this is you can see a star or a galaxy, and here instead you do not see. And I really invite you very, very warmly to help and look at these things, but you have to learn isodual theory before, otherwise it will be difficult to But here now, again, I've been looking at this for years. So the issue really is you see lots of this dark area in the universe. So the question is a real question that has to be answered quantitatively, not by politics or throwing judgment because I am such and such professor. No. Has to be judged in a serious way by examining all possibility, excluding those that are inconsistent, and so on. Ladies and gentlemen, this is far from being dust. This could be antimatter that simply cannot. We see nothing. We see nothing in our telescope because the converging lenses could be divergent for this thing. And in any case, look at the light. This is like ordinary light in the back. Look at the enormous existence of star and who knows, a galaxy in the back. It's extremely mysterious to me, at least, that no light comes through. So that's why I've been observing and thinking about, and I encourage you to think about, there are many of these things in the universe that are very, very mysterious, that until now they've been seen with preconceived, I assume Einstein theory, so therefore this is dust. But that's not science. Ladies, this is my view. So there is a realistic possibility that this indeed is antimatter, and therefore there exists a possibility that indeed in the universe there are antimatter galaxies that we do not see. In other words, everything that we have seen so far is matter galaxy. Yes, of course, it's unquestionable. But the question persists. Are some of those antimatter? I doubt. I doubt the one that we see. I doubt it. And so there is a possibility that there are antimatter galaxies that we simply have not seen at this moment. And until I see some experiment, I have to remain with my own doubt. Again, if this is if it is true that there are antimatter galaxies in the universe, then my talk yesterday, that the absence of the expansion and the acceleration of the expansion is wrong, because especially with experiment we prove that matter and antimatter repel each other. So I make this self-criticism just to illustrate the complexity of the universe, and we have to be careful before reaching final decision. I want to tell you, however, my instinct, what my instinct tells. My instinct tells that I have a great instinctive reluctance to accept the idea that the universe is only made up of matter. It will be in a kind of lack of democracy by the creator on one type of matter and not versus the other. So I will be extremely surprised if this asymmetry exists, and it's very likely we have not seen it. But then, if indeed antimatter exists in the universe, then we are talking about a true revolution, unbelievable implications in the very origin of the universe, and we are talking about also dramatically new cosmological conception. Let me give you a couple of glimpses. Let's make the limit assumption that we have an equal distribution throughout the universe of matter and antimatter. Then, ladies and gentlemen, for one observer, whether it is for matter observer or matter and antimatter observer, then the all total physical characteristics of the universe are identically zero. The universe has no total characteristics. The total energy is identically zero, total time identically zero, total momentum, and there are a number of people that start to think this way, because in this case, the act of creation of the universe implies no discontinuity. You see, I have difficulty in accepting the Big Bang because of the discontinuity at the time of creation, and so in this case you will have no discontinuity. Basically, you start with total energy zero. You have just separated into into matter and antimatter, but without any discontinuity at all at the act of creation. So there are cosmological and also philosophical, religiously, apparently you reach point of a mathematical treatment of creation without this continuity and all sorts of other interesting. Thank you for your time. Criticism, please.
I just wanted to know the gamma of annihilations of an electron and a positron. Are they normal gamma or are they isodual gamma? Because those ones we see now in one is gamma and one is an
Michele, Dr. Sacerdoti, this is a very deep question. Thank you for asking. The answer is I do not know. Because we have no because until now we have assumed that light is only one, and therefore gamma is only one. So, but once you start to see even the slightest possibility that you have a gamma and an isodual gamma, then the question is open. And we have no way of ascertaining until finally we find somebody like physicists like Professor Dehaene, others, of course, that who sits at the table and say, let's start testing whether this is a gamma or whether the isodual light exists or not. Then we can answer this question. But it's a very deep question, Michele. Thanks for asking.
No, because another thing is all revelation and detectors always see the two gammas. So this would say that there are two normal gammas.
But what they see the energy, and as I showed to you, you have the Hamiltonian, isodual Hamiltonian, which is negative definite, multiplied by the isodual product, gives you a positive energy. So the impact on a scintillator is visible. In other words, the impact is the same with Professor Dehaene. The key point of Professor Dehaene experiment is that the positron, when hitting a scintillator, shows something visible. That's the same for a gamma, identical. Keep in mind that in this theory, the positron is an isodual electron, has a negative energy. But again, when you do the calculation of isodual quantum mechanics, you'll end up with a positive energy in our world or a negative energy in the other world. So the question is far from being obvious. It's a very quick question, but my gut feelings and my knowledge is that at this moment, we cannot distinguish, which is, we don't have enough experimental information.
And another question, if there were antimatter galaxy and a matter galaxy, at the border, wouldn't there be annihilation? Wouldn't we be able to see a strong gamma emission? There would be some area in the universe in which matter-antimatter annihilate or meet.
There's another very important question. Thanks for asking, very deep. Again, Michele, my knowledge is very, very limited. I think for everybody, not only for me. Let's say, first the statement, when you have an antimatter galaxy, that is we assume it's entirely made of antimatter star. So there is no annihilation. In other words, again, it's a question of democracy. The whole thing is democracy. In our galaxy, it's obvious we only have matter, otherwise we will see flashes everywhere. This was the discussion also with Dr. Berkowitz, our belt, asteroid belts. If there were a mixture of matter and antimatter asteroid, we will see all sorts of flashes. None of this is recorded. So the galaxy, if an antimatter galaxy exists, has to be the same as our name, made of antimatter stars. Now, but after having said so, however, our universe is very dynamical. And so now, if you look at some of the episodes in our recorded history, some of them, for instance, are interpreted as a supernova. Not necessarily they are supernova. They could be collision of this was supposed to be the talk which has been annulled with Professor Animalou. He's not here. I don't have time to prepare. There are not necessarily the evidence that the supernova is entirely due to the star at the dying. It's very questionable. There are many questions, open issue. It's possible, of course, not all of them, but it's possible that some of this episode have created this. Let me put it in a different way. If you look at the calculations, the energy in some of those supernova claim to be supernova, the energy is so astronomical that I personally cannot I cannot accept it in any case, that there's an immense number of energy that is, I don't know, 10 to the 100 joules, this type of things, is due to internal nuclear fusion inside the star when the star is dying. I cannot accept it because we, for many reasons. Well, one reason is the following. We have measured in our laboratory in Florida, the synthesis of the silica, confirmed by Professor Leon Ying in our new nuclear fusion without radiation. So if we have synthesized the silica, our little guys, we have synthesized silica, I exclude that a star cannot synthesize heavy elements. In any case, look at the availability of heavy elements in our galaxy. It's so widespread that cannot be represented by the hypothesis that heavy elements are created by supernova. No, that I rejected because it's disproved by evidence. So the question then persists: where is that energy coming from? There is an enormous amount of energy. One solution is the collision of matter and antimatter star. Yes, then you'll have this type of. The other alternative is, however, the complexity of nature. You see, the synthesis of the neutron requires 1 MeV, unless it comes from somewhere. A star will never start to produce light. Never, because it loses 10 to 100 MeV per second when it starts synthesizing its neutrons. So a star will never be born. This majestic phenomenon of nature, of God. I believe in God. It will never occur. So, but then it's possible when, incidentally, until there is nuclear fusion inside a star, I cannot accept I cannot accept the collapse. I'm sorry, because it is against all my instinct, calculations. So until there is nuclear fusion, but then when the nuclear fusion have synthesized, where is this enormous energy astronomical energy coming from? We have to address those issues, and the answer will not be in 20th century physics. Let's be honest. Sure, we consider for respect the 20th century physics, but we have to add new physics. So besides the supernova collision of stars, there is a possibility that the heater provides energy to a star at the moment of birth, synthesis of the neutron. That's the beginning of the fusion. And at its end, when this collapse, then we are talking about 10 to 100 neutrons to be synthesized per second. Then you see this enormous amount of energy that is absorbed. So there are very deep questions of which you can only list the alternative. But thanks for asking the question. Yes, please.
I have two questions. The first is very much related to my speaker before. When, light from stars and galaxies and anti-galaxies is different. Let's assume that. Now when an electron meets a positron, they annihilate and we get 2 electrons, I've said. What happens to the photons or light from the stars when it meets the light of the other? If there's the photon and the antiphoton, do they interact? That's the first question. And the second one is, you avoid by your assumptions the question of creation. You mentioned it later. But then you have another problem. That's the one of separation, which is equally hard, I believe.
That's a very deep question. Let me try to address the first question. The first is a very important question because I hope and pray it could be open to some experimental verification. Namely, we have electron-positron annihilation produce 2 gamma. Isodual theory predicts that one of the two gamma is isodual because of the conservation of iso-self duality. We start at the beginning with the charge and its antiparticle, charged particle and its antiparticle. We expect but it's not necessarily verified, experimental. But the point persists. Now, in the future, if we have sufficiently accurate neutron interferometric measurement, and this beautiful machinery that's not been built for acceleration to enormous energy, now useless in my view, or at least of marginal relevance for the future, From now on, until now it's okay. I was in favor of the experiment. From now on, I'm against any of this additional search. Now, if you use some of those machines and you have enough length, then with neutron interferometry in the future, we should be able to resolve the issue whether both gammas are ordinary gammas or one of them is also one will be repelled by gravity, the other will be accelerated. But the question remains open. Are they the same gamma or they are different gammas? And also the level of polarization, etc., etc. The other question, the epistemological, beautiful question, and I appreciate you asking. And again, if you are a religious person, you tend to avoid the singularity at the act of creation, because it's not, it's instinctive. The Bible didn't say that God created the universe with a big bang. No, actually, God says He created light first. But in any case, the point persists that if we can have an act of creation of this enormity of the universe without a singularity at the beginning, I think this has some significance, not only physical, but even from a religious viewpoint. I hope I answer your question to my best. Well, the act of creation will be, there is no discontinuity. This type of, are called iso-self-dual cosmology, with zero of everything. All total physical characteristics of the universe are zero before and after. The act of creation is reduced to the separation of matter and antimatter, just a separation. But it's not a creation. You are correct in saying that there is no creation. That's why there is no discontinuity, because the universe is too big. It is too big to allow, only by separating. And that's why the ether is conceived as being enormous energy, density, in 1 centimeter cube, imagine throughout the universe, with the coexistence of positive and negative energy, coexistence of the Minkowskian and isodual Minkowski space, coexisting one inside the other. I'm sorry? Forever. And then out of this you extract matter and antimatter. You can extract everything from the ether. Once you know the mechanism of extracting energy, that's why there is now a flurry of research going on in various countries, how to extract energy from, not from the vacuum, not 0-point energy, no, there's something different. How we extract, how we can duplicate the mechanism of synthesis of the neutron, which is getting close to 1 MeV from nowhere, how we can duplicate it and have it as a source of propulsion, or this is now a real problem. Is being investigated seriously. Incidentally, thank you for asking the question. Incidentally, there are insisting rumors that I was financed by the Air Force, United States Air Force, for several years, but not for military research. I became a U.S. citizen because in appreciation of this support. But there are rumors insisting rumors that U.S. Air Force has indeed a vehicle that can move and without fuel tank. They claims that are available now. They are available now. Of course, ultra secret Area 51, but those are rumors. But listen, if this thing that we are saying, extracting energy from the ether, from the neutron, is true, yes, they have a craft doing the same. It becomes very, very, very feasible. It's just a technological question. How do you multiply, you control it, and so on? It's the principle of extracting energy from. Incidentally, that's why we did the isotopy of Hilbert spaces. Otherwise, you would not be able to do it. No calculation that I know. I hope I didn't push too much beyond the level of science into epistemology.
Okay, now the order of the question is this. Professor Trell, Professor Johansson, Professor Beckwith, Professor Moscarion, and Professor Burischi. Okay, Professor Trell.
So let's do it quickly then. I don't want to, the next topic, but it's very interesting by Professor.
Yeah. Thank you very much. Thank you very much for opportunity. Well, it seems that our senses are made for absorbing things. So they will lead to a kind of retardation. But I wonder, antimatter photons, would they perhaps be detected by emission instead processes?
By
emission.
yes, it's a possibility. Yes,
Yeah.
it's a possibility. Yes,
Because all our senses and instruments to amplify them are made for receiving photons and thus being absorbed. But there is an inverse of that, namely that emit photons instead, and they should be reflected by an acceleration in the detection device.
with the understanding that depending on the theory, you can have all sort of conjugation. Also keep in mind that if what we said here is correct, we will not see an isodual light will not reach our retina, will die into our crystalline. And assuming it goes through, it can be, the crystalline becomes a phenomenon of dilating, is diverging the light. So we will not necessarily we see with our...
No, but I think antiphotons, if they would tend to be attractive, so to say.
Absorbed.
Yeah.
Yes, absorbed,
so
but
you
not
could-
necessarily you reach the retina.
Yes.
So even at the level of the eye,
Yes.
the question whether we can see very dim, of course,
Yes.
so an antimatter star
Yes.
is questionable, even at the level of the eye, let alone of the instrument.
Yes. Yeah. Well,
Thank you.
that's a little-
Perhaps, Professor Trell, you should discuss this with our master experimentalist, Professor De Haan, because maybe we can come up with some
Professor
experiment.
Johnston.
Yes, an open question here. If we or you consider the notion of iso-self duality and the notion of light also having a bound state of iso-dual light, iso-self dual light. In the bound state of iso-self dual light, could it be possible that would be the state of light necessary to detect both objects of antimatter and matter?
Professor Johansen, we do not know of a bound state for light. And there is a total democracy, so at this moment we have no grounds to create we can create a bound state that will produce light and a bound state that will produce isodual light. Yes, this I think not today, but hopefully in the future will be something, if that is feasible, then your question becomes within the experimental range of verification, yes, yeah. But you see the many unknowns. This is really the first workshop on antimatter astrophysics because the list of unknown is so big. But that's the beauty, that's why I'm interested. Things
Professor Beckwith.
Thank you, Dr. Santilli. I'm going to ask a very naive question.
Stay close to the microphone.
I'm going to ask a very naive question. It has to do with the relative amounts of matter and antimatter that may exist in the universe. Assume you have some sort of a baryon type of number for matter, and you have baryon type of number for antimatter.
Yes.
Could you, in some sense, have some sort of a fluctuation of a ratio between the two that in some cases might mimic some of the cosmological fluctuations that people have said might have been connected with inflation or other things, or are you going to have a relatively fixed ratio of matter to antimatter to one another?
It's a magnificent question in which I do not know the answer at this moment, because this we'll discuss after Dr. Sacerdoti the talk about this antiproton that are presumably created at CERN.
Well, the reason I'm asking this is because of the fact is that it's well known, so to speak, which is there's an accumulation of structure within galaxies. And so what we might be seeing in terms of cosmological evolution in terms of galaxies might just simply be, there might be a conservation to say the number of matter and antimatter, but the different type of domain structures might evolve and change over time.
Yes.
Now, as the domain structures are evolving and changing over time, it might, in some sense, give some sort of an illusion, if you want to refer to it, as to what you might call a definite cosmological cycle. Whereas what we really are seeing is not so much an evolution of a cosmological cycle, but we're seeing what you might call the evolution of cosmological structure, but the relative, let's say, from disorder to order or something like that in a periodic cycle. But we would see, though, we might see
Yeah,
some sort of a ratio.
No, but back to your question, you see, the question of baryonic number conservation or
Yes,
violation
baryonic.
has to be addressed, however, at a cosmological level, not inside a little accelerator, no matter how big here is on
Yes.
Earth. So you see, we have no information of even addressing the issue at the cosmological level. Locally, if there are local variation, I concur less.
Well, you
No
might
interest.
see some sort of a natural, for instance, of matter and antimatter, something
Not-
very close to
not-
Hoyle's steady state.
Not necessarily, because it goes back to the act of creation. If the act of creation is based on democracy between the two and then
Oh,
the
I see
separation,
your point.
then no. There is no. Whatever we do here on Earth, I have a great reservation on antimatter. Great, yes.
Professor Moskaliuk.
I have a short comment on the question. A comment to previous questions about detecting the photons, electromagnetic waves from annihilation, for example, of proton, positron. It is possible to fix. If this annihilation is occur in a locally anisotropic space, so this electromagnetic wave will be linear polarized.
Yes.
So I will show in my talk this.
Yes.
And my question is actually a big part of information in electromagnetic waves saved in polarization effects. So that is question is why you don't considering polarization of your gamma quant, which is produced by antimatter. In this sense, you will be considering more successful and many new effects.
Professor Moskaliuk, this is a beautiful proposal. Actually, the paper which I wrote on publishing the proceedings of the Cepino conference 1996, was a question mark, does the antimatter emits a new light? The first thing I looked at the polarization, and you look at the isoduality of Maxwell equation, and indeed the first difference is precisely on polarization, but there are others with respect to parity. I even forgot some of them, it's about more than 10 years. So, but I agree completely. I only here focus the attention on the most visible implication, which is the repulsion of antimatter light by prediction of repulsion by antimatter light of a matter field. But there are other ways in which the distinction is, and those differences are unavoidable. Also because remember, I just touched briefly, I couldn't elaborate, that isodual, when you map the space, the coordinate x, under isoduality, this has been shown not by me, by others, that it is different than space inversion. Yes. So there are a number of ways in which, yes, you are correct in bringing attention to polarization. You have an isodual polarization, which you have to look at the structure and see how to detect it. Even how to detect it experimentally, we do not know. The attraction of repulsion is the one that we know for sure how to measure. There's other intrinsic feature of this predicted isodual light. Even the instruments we do not know. Look at the instruments to detect an antimatter star. We don't know which is the correct instrument. Yes.
Professor Burinsky.
It's really a very interesting question and very interesting discussion and very deep questions.
Thank you.
But what I would like to pay attention, maybe comment about in the beginning of your talk.
Can you speak louder, please?
In the beginning of your talk, you write that energy is equal h nu, and isodual energy is equal minus h nu. And you this sign minus state in correspondence with h. I would like to pay attention that there is alternative possibility. If you take this sign minus not to h, but to frequency, it will be very interesting. It seems that h is the same, but in fact, isodual photons it is simply photons of negative frequency and negative energy. In this case, we get some kind of interesting possibility that light is really the same, but only positive and negative frequency at corresponding positive negative frequency. It seems it is very natural way to standard traditional point of view. And maybe some contradiction will be disappear.
Your point is very deep, and indeed it's a possibility. That's why I only put question marks. In other words, if I can rephrase your point, which is very deep, namely your point, you're saying, okay, let's admit that in the energy we have three entities. We have Planck constant, the product, and the frequency. And all three of them have to be subjected to isoduality, you get a minus. However, your point is okay, but this is referred to a negative energy in my language. So positive light with positive energy refer to a positive unit is perfectly equivalent, this is your point, in my rephrasing, perfectly equivalent to a light with negative energy that is referred to a negative unit of energy. Therefore, the two lights are ultimately equivalent. This is a very deep issue in which, of course, we have no way of providing a definite answer. The only point of the prediction of a physical difference are with respect to gravitation. That one light is attracted and the other. It's impossible that both light are attracted by gravity. No, with a bending. That is impossible. One is bent and the other is reflected. Incidentally, I've been told that there are the astrophysical evidence that has been suppressed in the referee journal that of repulsion, of gravitational repulsion, of light anti-bending. Apparently, those phenomena have been seen in astrophysics, but systematically rejected by referees, and because in violation of Einstein, and so there are no chance of appearing. Let's hope that at least now they can have some more attention and open, or a little bit more open mind. Otherwise, we'll remain frozen to the past century. But I agree, your question is very deep. Ultimately, despite this thing, it may be possible that both light are attracted. If that's the case, then we will be able to see an antimatter asteroids with matter light. Yes, because by compatibility you reach the refraction, reflection, and then the answer is yes. But we do not know now for sure that that's the way. In other words, my whole effort is to stimulate your imagination and help in solving those problems, and considering at the stage of our knowledge, we can only list all possibilities. The future will tell us which is the way to go. Whatever the outcome, I will tell you this will be substantial indeed. We are in the 21st century. Yes, we are no longer in the 20th century. I think there is another question.
Professor Gill.
Yeah, Ruggiero, is it possible to, seems like it would be possible to put together a telescope that, a diverging lens at the receiver side of the telescope to look at the dust clouds, or I should say the dark cloud?
Professor Gill, I have to come down and hug you, because indeed, let me tell you openly, we are among friends, don't quote me, but I did make this proposal to an astrophysicist, to an astronomer. I was considered to be totally demented banana, and therefore instantly disqualified. I exclude. In other words, yes, that's what we should do. Put a diverging lens at the end of an ordinary telescope and look at the sky. Because that's what then we can say, okay, now we're sure that this does not work and the antimatter galaxy do not exist. Then we'll see. But remember what happened to the Galileo telescope. The cardinals refuse even to look at it. So we have exactly the same things. Then if you have a big guy responsible for an astrophysics laboratory who does something like this, he will lose his job in a flash. Instantly was thrown out and replaced just because of suspecting that Einstein theory could be violated or not being dominating the entire universe. So this is the situation at this moment. But yes, I would love to do that. And maybe we can find, Professor Dehan, maybe you can, or some of you who have worked in optics, maybe we can build our own telescope, put a diverging lens, and put both converging and diverging lens, and look at the sky and see what we see, and then compare with the converging and diverging lens. Thank you for proposing because that's a real thing. Let's do it and then reach conclusion. Thank you.
Professor Moskaliuk and then Professor Udriste.
I should comment to the comment of Professor Burinsky. Actually, Professor Feynman noted that if you write equation of motion for the antiparticles and any formulas, they differ from the equation for the particles only to putting time negative. So in this sense, time, if you put negative, you will receive, it's not Planck constant have to be negative, only time, and you will receive all correct formulas. Thank you.
Well, Professor Moskaliuk, what you say, this idea of Stueckelberg was a very nice Jewish physicist in Switzerland. He was the first. We have to honor Stueckelberg because he was the first to give a plausible idea solution for the annihilation. And his idea, not ours, was the antiparticle travel backward in time. And therefore, annihilation was due to the annihilation of time. Annihilation of a particle, an antiparticle annihilates. Very unfortunately, Professor Stueckelberger's idea were rejected by, including Feynman, rejected because of the acausal behavior of a particle with negative time. One of the objectives of isodual theory is kind of honor Stueckelberger because the moment you refer negative time to a negative unit, you assume, you recover causal. All the historical objection for antiparticle moving backward in time, they crumble. You cannot even introduce them. They are dead, trashed out. So we go back to this original proposal and we have honored the originators as we hope the follower will do with us, which is debatable. But back to the issue, however, but there is one point in which I have to disagree with you. If you do only the conjugation of time, you will have all sorts of problems. You got to conjugate everything. Once you have conjugated time by consistency, you need a negative unit. How do you reach a negative unit? By an anti-isomorphism. Anti-Hermitian isomorphism. But then why do it only for the unit of time and not for the rest? You have all sorts of inconsistencies. So you look at the Newton equation for antiparticle. Everything, not only time. Yes, time is crucial. And I'm so glad you brought this point. But the rest has to be differential, mass, the product, the quotient, and so on. Otherwise you have inconsistencies. That's for what I know, Professor Moskaliuk, which is rather limited.
Professor Udriste.
With respect to this subject, I want to make a small comment. In my opinion, depend what we think to see in the problem. Because if we want to see something which in differential geometry is holonomic, manifold, all these presentations, all these talks refer to this point of view. But if we want to see a system which is non-holonomic, what we see? In my opinion, you will see a bundle.
You will see what? Repeat, please.
Bundle.
Oh, I see bundle, yes.
Yes. What is the meaning? For example, if you judge in 5 dimension, and you will have a 4-dimensional non-holonomic constraint, what you will see? You will see the tangent space is 4-dimensional. So it's impossible without some experiments to see this. But we can see, for example, evolutions, 1-dimensional evolutions, and 2-dimensional evolutions, but they are not unique through a point. So you will see a bundle. And I think this figure, which was very nice colored, is a bundle.
Yes.
It is not a usual corp.
Yes, this is definitely.
This is sure.
Yes.
And another comment is regarding this kind of telescope. Usually we have in mind the classical telescope. But some years ago in Polytechnic University of Bucharest, together one of my friends, which was physician, we discovered that when you speak about receiver and emitter, optimal receiver, optimal emitter, you can have different kind of situations. For example, you have emitter like a surface, receiver optimal like a surface. You have emitter like a surface, receiver like wires. Non-holonomic wires, not any kind of wires. Nobody till now realized this kind of antenna. But I know how can be realized.
That's great.
And in this way, for example, if you look at a bundle, it's possible there to be a mirror like wires. Let's say non-holonomic, I don't know. Then the best receiver must be wires, distributed in a suitable way.
Yes.
In order to recover something. Because it's not enough what is in our mind. Depends how we judge, in fact, about this subject. And in my opinion, this kind of, the difference between holonomic and non-holonomic can be very special in this theory.
Well, both issues are very, very deep. Regarding the second, this experimental, I will recommend you to discuss with Professor Dehaene. But definitely, I encourage you. Regarding the first issue that you raised and regarding the bond, this is very deep. Ladies and gentlemen, by using what Professor Udriste indicated, and you can derive doubts as to whether the antiproton claimed to be produced at CERN are really antiproton. Since they have the mass close to the proton and the charge is opposite, they claim it is antiproton. Ladies and gentlemen, it's not necessarily the case. We'll discuss this after Professor Sacerdoti the talk.
Okay, other questions?
Okay,
Thank you very much, Professor Santilli.
Thank you for all beautiful questions. Thank you.